All right, let's learn more formally about Butterworth filters today, and maybe this one won't get away from me. All right, so the Butterworth filter is a medium Q filter used in designs that require the amplitude response of the filter to be as flat as possible. In fact, the Butterworth filter, out of all of the 4 different types of passive filters, has what's called a maximally flat response, meaning that it never introduces any ripple whatsoever. So this is widely used in filtering in control systems where you want to avoid peaking or having a portion of your response to where it spikes up, because that can turn your negative feedback control loop into a positive feedback control loop, which would turn your system unstable. So Butterworth filters are used extensively in control systems, and then Chebyshev filters, which we're going to talk about in our next class meeting, are used a lot more in communication systems. But anyway, so the attenuation provided by a Butterworth filter, excuse me, is given by the following relationship. So this is our attenuation measured in decibels. So that's AdB is 10 times the log of 1 plus omega over omega c, where omega c is our desired cutoff frequency, and that omega over omega c is raised to the 2nth power. Okay, so let's explicitly say where omega is the frequency at which attenuation is desired, omega c is the cutoff frequency of the filter, and n is the order of the filter. So we can use this relationship to determine filter order for a desired performance. So let's say, for example, that we want to know the minimum order required. So let's write this down. What is the minimum order required to achieve at least 50 decibels of attenuation at 150 megahertz if the filter's cutoff frequency is 50 megahertz. So using the equation from above, our attenuation in decibels is 50 dB. And this is going to be equal to, 10, better, log of 1 plus 2 pi times our frequency of interest. So that's 150 megahertz over our cutoff frequency, 2 pi times 50 megahertz to the 2nth power. We can see very easily that the 2 pi's cancel each other out and the megahertzes cancel each other out, and 150 over 50 just looks like, actually, I shouldn't have done that. 150 over 50 is 3. So this simplifies down to 10 log of 1 plus 3 to the 2n. So now we've got to rearrange this guy and solve for n, right? So I could divide both sides by 10, leaving me with 5 is equal to just the log of 1 plus 3 to the 2n. If I do 10 to the on both sides, that's going to get rid of my log. So that would look like 10 to the 5 is equal to 1 plus 3 to the 2n, or approximately 10 to the 5 is approximately 3 to the 2n, or 9 to the nth power. Are we okay with the math that went on there? So if we solve this explicitly, we would find that n would have to equal 5.240. Now, it's not possible for us to have a filter order that isn't an integer. So we would actually just need to round up. We will always round up because we want to make sure that we have at least 50 decibels of attenuation. So a 5th order filter would not provide us the attenuation we need at our particular frequency of interest, but a 6th order filter will actually provide us more attenuation that we need, since our filter order for exact would be 5.240. Okay. So let's take this and design I don't know why I put example number 6 there. That's not right. A 6th order Butterworth filter, always up, always up. And again, it's because if we need at least 50 decibels of attenuation, if we used n is equal to 5, we would not hit 50 dB of attenuation. In fact, let's do that really quickly, right? So if we just put in n is equal to 5, let me just do this as a quick thing here. So when n is equal to 5, we would have 10 times the log of 1 plus 3 to the 2 times 5. So that gives me 47.712 dB of attenuation, which is less than our design requirements. So a fifth order filter would not get us where we needed. For n is equal to 6, we would have 10 times the log of 1 plus 6. 57.2545, so let's call that 57.255 dB, which exceeds our design requirement, right? The order of our filter always has to be an integer because it's just the number of energy storage elements, so we can't have a quarter of an inductor or a quarter of a capacitor or anything like that. All right, so let's design a 6-order Butterworth filter with RS is equal to RL is equal to 50 ohms. And let's say that our cutoff frequency FC is 50 megahertz, meaning effectively we are designing the filter that would meet the design requirements of our previous problem. Okay. So 2 different things that we could do, right? So just for the sake of argument, we could use our standard topology. Right. So we know that this is going to be 50 ohms and this is going to be 50 ohms. So let me just put those in. So that's RS and RL. This guy is going to be C1, L2, C3, L4, C5, L6, like so. And so we would just get our handy dandy Butterworth filter table that you guys should all have. And if you don't have one, come up here and get one. Got them in class last Friday. So I'm just looking for n is equal to 6. So my nominal values, let's just put them down here from my table, are C1 is equal to 0.518 farads. L2 is equal to 1.414 henries. C3 is equal to 1.932 farads. L4 is equal to 1.932 henries. C5 is 1.414 farads. And L6 is 0.518 henries. And now we need to figure out how to scale these things, right? So based on our design criteria, we know that our magnitude scaling factor, Km, is just going to be 50 ohms over 1 ohms is 50. And we know that our frequency scaling factor, Kf, is going to be 2 pi times 50 times 10 to the 6th radians per second over 1 radian per second is pi times 10 to the 8th. We okay with all that kind of good stuff, right? So just to be clear here, the reason why I'm putting 1 ohm down here is because my table says RS is equal to RL is equal to 1 ohm, and 1 radian per second here is because the table is valid for omega C is equal to 1 radian per second. All right. So now it's just some math, okay? So let's scroll down here really quickly. So our scaled version of C1 is going to be C1 over Km Kf, or 0.518 farads divided by 50 times pi times 10 to the 8, and I get 32.977 picofarads. L2 prime is going to be Km over Kf times L2. So that's going to look like 50 times 1.414 Henry all over pi times 10 to the 8. And that gives me 225.045 nanohenry. C3, we use the exact same relationship. So that's C3 over Km Kf. So that's going to look like 1.932 farads over 50 times pi times 10 to the 8, or 122.995 picofarads. L4 is Km over Kf times L4. So that's, it is indeed 10 to the minus 12. So L4 was 1.932. Pi times 10 to the 8th gives me 307.487 nanohenries. C5 prime, once again, C5 over Km Kf. That's 1.414 farads over 50 times pi times 10 to the 8 is 90.018 picofarad. And lastly, L6 prime would be Km over Kf times L6, or 50 times 0.518 henries all over pi times 10 to the 8, which I get to be 82.442 nanohenries. I also have worked out here, for what it's worth, the numbers that we would get if we used this guy. So I'll just show this to you. This is from the bottom thing on the table. So if we had this representation instead, where we have series inductance and then shunt capacitance. And I'm not going to go through and bore you guys with the math. We would have 84.442 nanohenries, 90.018 picofarads, 307.487 nanohenries, 122.995 picofarads, 225.045 nanohenries, and 32.977 picofarads. So it's effectively the exact same numbers, but their order is opposite. So let's throw this into LT Spice and just see whether or not we've met our design criteria, right? So using these particular values, I can find my damn mouse. Here we go. So here's my voltage source. Yes, that'll work. Then let's see. Inductor there, and there, and there. Capacitor here, and here, and here. Last resistor goes here. This is 50. Just running back through these numbers real quick. 32.977 pico. 225.045 nano. 122.995 pico. 307.487 nano. 90.018 pico, and 82.442 nano. Give myself a stub of wire, ground, AC analysis, decade. Let's do 1,000,000 points per decade. Let's start it at 1 kilohertz. Let's end it at 1 gigahertz. And if we look at our output voltage here, let me move this thing out of the way. So we're at -6 dB all the way up to here. And then when we hit -9 dB, we're at just over 50 megahertz, but there's some rounding going on there. So anyway, So we have a corner frequency at 50 megahertz like we designed for. Do we have at least 50 decibels of attenuation at 150 megahertz? So what we should be expecting is a greater, a magnitude of at least negative 56 dB when we get to 150 megahertz. So there we go. So at 150.79 megahertz, we're at negative 63. And like I said, we should be just greater than negative 56. So this seems to check out. Okay. So we have designed things correctly. We talked about at the end of our last class meeting what would happen if we wanted to design where our resistors, our source and load resistor were not the same. And that's where the second table and all of that kind of good stuff comes in. Our magnitude scaling factor in that case is based on what our load resistance is, which I found out by process of elimination based on the mistake I made last class. So that's fine and dandy. So let's talk about something slightly more interesting here. Okay. So let me hide this thing again. Okay. So the table that we were given, or the tables that we were given, only talk about low pass filters, which is fine and dandy, but we don't always necessarily want a low pass filter. So let's talk about how we can use this table for high pass filters and band pass filters and band stop filters and stuff like that. Okay. So I'm just going to do this as a third order filter representation, and then we'll go from there. Okay. So let's say that we have, or actually, let's just put it like this. So for a low pass filter, we would have this circuit right here, right? Here's our input voltage. Here's our source resistance. We have our shunt capacitance C1, L2, C3, and then our load resistance over here. So let me ask you guys, because it seems intuitive-ish to me, at least to some extent. How do you think we would convert this circuit from a low pass filter into a high pass filter? Let's start there. Anybody have any thoughts? Say that louder, please. So we're not going to flip well, I don't know what you mean by geometry, but effectively everywhere we have a capacitor, we're going to replace it with an inductor, and everywhere we have an inductor, we're going to replace it with a capacitor, right? So for a high pass filter, our circuit would look something like this. So here's our source resistance. Here's an inductance, capacitance, inductance, and then here's our load resistance, right? Now, here's where it gets interesting, or at least to me. The value of this inductance here is just going to be 1 over C1, the reciprocal of the capacitance from our table. Similarly, the value of this capacitance will be 1 over L2. The value of this inductance over here will be 1 over C3. So effectively, all we're doing is swapping the element and then taking the reciprocal from our table. So the reason why this works, at least from a dimensional or unit standpoint, so let's look at our capacitor, right? So if we have a capacitance of measured in amp seconds per volt, the reciprocal of that is that's going to look like a volt over amp seconds. The volt per amp thing, like if we would have had a second up here, that's going to be the exact same thing as a Henry, effectively. So by just using the reciprocals of the units, it comes out to be the correct thing as well, okay? So low pass filter and high pass filter, pretty straightforward. We simply swap our elements around and then take the reciprocals, okay? What about a band pass filter? It does. So let me prove it. So I've already got the band pass and band stop on here, but let's just run a quick simulation. So here's our low pass filter, and we have a cutoff frequency. So this is designed for omega C is equal to 1, so 159 millihertz, like we saw in our last class meeting. If I look at the output of my high pass filter, it's at the exact same place, okay? So flipping it like that leaves our cutoff frequency at 1 radian per second. Yes. So the dashed line is our phase response. So the solid line is magnitude response, dashed line is our phase response. Exact same thing it was back in circuits 2. We're only really concerning ourselves with the amplitude response here, but we can say that this is literally the exact same shape of frequency response, except that it's flipped around. Okay. So bandpass filter. So for a bandpass filter, we are effectively going to make the following changes. So for our shunt branches or our vertical branches, we are just going to add an element in parallel. And for our horizontal branches, we're going to add an element in series. Okay. So we've got our excitation source. Here's our resistance, which is not part of our filter. So here, we're going to have a capacitor, and then directly in parallel with that capacitor, we're going to put an inductor. And then this is the inductance from our low pass filter. And directly in series with that, we're going to put a capacitor. So we just add one of the other energy storage elements, okay? So from our low pass filter here, our third element, so let's call this C1, L2, this guy is going to be C3. So in parallel with C3, we're going to put some inductance. And then there's our load resistance, like so. And the element values for these added components are literally just the values from our high pass filter. So we're going to have C1 in parallel with a 1 over C1 inductance. We're going to have L2 in series with a 1 over L2 capacitance. And we're going to have C3 in parallel with a 1 over C3 inductance. So let's look at the frequency response for that real quick, okay? Get my keyboard here so I can just delete some things. Move this out of the way. So let's delete this guy and delete this guy. And we just want to look at this frequency response, okay? So does this look like a bandpass filter response? It definitely does to me. So let's make a couple of observations here really quickly. So here I'm in the middle of my pass band, or as close as I can get to the middle, okay? So our resonant frequency, or omega naught, for our filter is at that 159 millihertz. So it's effectively still the omega c is equal to 1 radian per second that we were interested in, okay? So now our cutoff frequency is our resonant frequency. It's the middle of our pass band, okay? If we look at our low pass part, so what we're looking for is the frequency at which we hit -9 dBs, because our peak value is -6 dB. We're at, let's call it 98.5 millihertz. So you guys write that down. F low is 98.5 millihertz. And now we're going to go to the other side. And we're again looking for -9 dB or so. $257.4 millihertz. So that's F high. Take the difference of those two things. So omega high, or F high minus F low. So it should be the exact same thing as omega naught, effectively. So our bandwidth and our resonant frequency are the same right now, okay? So we have 159-ish millihertz of bandwidth, and we have a center frequency of 159 millihertz as well. Or we have a bandwidth of 1 radian per second and a center frequency of 1 radian per second. Yes. So, no, the resonant frequency is a single frequency. So let me better explain that. Let me draw a picture here real quick. Okay. So if we look at the frequency response of this guy, so here's the magnitude of our transfer function measured in decibels. And here is omega, right? So let's just put -6 dB right here, and let's put omega naught right here. So we're roughly flat in this region. Omega naught is the middle of our passband, okay? And then we're going to fall off at some particular slope, like so. So if this guy right here corresponded to -9 decibels, then the width of our passband is also the same thing as our resonant frequency. Does that better clarify things? Okay. So this is all fine and dandy, but chances are that we're not always going to want the bandwidth of our bandpass filter to be the same thing as its resonant frequency. We're probably going to want it to be smaller, because this is passing a pretty broad range depending on what our resonant frequency is. So we'll talk about how to scale that and all that kind of stuff here in a moment with another design thing. But now let's look at a band stop filter, okay? So for the band stop filter, we are effectively going to do what we just did, except exactly the opposite. So everywhere we put an element in parallel, we're now going to put one in series, and everywhere we put an element in series, we're now going to put one in parallel. So it would look something like this. So here's our normal low-pass filter capacitance C1. And now in series with that, I'm going to put an inductance that is 1 over C1. This is a band stop filter. Band stop or notch filter, okay? Over here, where we would normally have just an inductance, I'm going to put an inductance L1, excuse me, L2, in parallel with a capacitance 1 over L2. Over here, where we would normally have for our low pass filter design, a capacitance C3, I'm going to place an inductance 1 over C3 in series. And then here is my resistance RL. Okay. And let's look at the frequency response of this guy. Okay. So right now, I've got my band pass filters frequency response up on the screen. And so now I'm just going to click this node, and that's going to give me my band stop filters frequency response. Let me change this color to red. I think you guys have difficulty seeing that blue. Oops, that didn't work because I pressed the wrong thing. So we have the exact same situation. Now the center of our stop band is at omega naught, and we once again have a bandwidth. So the width of our stop band is also omega naught, okay? So let's talk about how we are going to fix that. And that's going to be what's called bandwidth scaling, okay? So we're going to design a filter. We're going to do it a third order. Butterworth band pass filter with a center frequency of 100 kilohertz. And a bandwidth of 0.1 times our center frequency. So effectively 10 kilohertz. Okay. And we're going to say that RS and RL are 50 ohms. Okay. So let's figure out our parameters here. So our magnitude scaling parameter is 50 ohms over 1 ohms. So that's literally just 50. Nothing new there whatsoever. Our frequency scaling factor, KF, is going to be 2 pi times 100 kilohertz over 1 radian per second. So this is going to come out to be 2 pi times 10 to the 5. And I'm going to introduce a new scaling factor here, KB. That is literally just our bandwidth divided by our center frequency. So this gives us 0.1. Okay. Since we're dealing with a third order filter, C1 from our table is literally 1 farad. L2 from our table is 2 henries. And C3 from our table is 1 farad. So if we weren't worried about our bandwidth scaling, C1 would be, or excuse me, C1 scaled would be C1 over KMKF, right? Based on what we did in our last lecture, what we did in our previous examples and all of that kind of good stuff, okay? So that's literally just going to be, in this case, 31.831 nanofarads. With our bandwidth scaling in place as well, so I'm going to call this C1 double prime, and I'm just going to make a note up here. With bandwidth scaling, this is just C1 prime over KB. So this is going to come out to be 318.310 nanofarads, because dividing by a factor of 0.1 is the same thing as multiplying by a factor of 10, okay? Nothing wild or crazy there, okay? I'm going to give myself some space. So let's do L2 prime. So just to be clear here, this would be Km over Kf times L2. Plugging in our numbers, this would come out to be 159.155 microhenries, excuse me. And L2 double prime, so this is with our bandwidth scaling, is just going to be L2 prime over KB. So this comes out to be 1.592 millifarads. And giving myself some space. Millihenries, thank you. It's all going into my LT spice the same. I'm just using the little m, but thank you. And then lastly here, we would have C3 prime would be C3 over Km Kf. And plugging in these numbers, I would get that same 31.831 nanofarads. And so C3 double prime would be C3 prime over our bandwidth scaling factor, giving me once again 318.310 nanofarads. So for our quote unquote normal elements, meaning the ones that we just ripped straight from our low pass filter table, it looks like all we're doing is the same basic scaling that we've done before, and then we're dividing by our bandwidth scaling factor, okay? Now let's do the other elements, okay? So L1 prime, so this is an inductance. We've scaled all of our inductances by doing Km over Kf, and now we're going to multiply by 1 over C1. So if we plug these values in, that's going to be 79.577 microhenries. Okay. So to get L1 double prime, so this is our inductance in parallel with the capacitance C1. What we're going to do now is we're going to do KB times L1 prime. So for our normal elements, or our low pass filter elements, we divide by KB. For our high pass filter elements, we multiply by KB, okay? And so this is going to come out to be 7.958 microhenry. Okay. For our capacitance C2 prime, that's going to look like 1 over Km Kf, because that's how we've scaled all of our capacitors. And then our capacitor value is 1 over L2. So plugging in our numbers there, we get 15.915 nanofarads. And then C2 double prime is just KB times C2 prime. So 1.592 nanofarads. Okay. And then lastly, we have our inductance L3 prime. So that's Km over Kf times 1 over C3, giving me 79.577 microhenries, excuse me. And then L3 double prime is KB times L3 prime is 7.958 microhenries. So there was a lot of things going on here. So I just want to clarify what's happening. For all of our normal quote unquote scaling without the bandwidth scaling, anytime we have a capacitance, we're multiplying by 1 over Km KB, or excuse me, 1 over Km Kf. Anytime we have an inductance, we're multiplying by Km over Kf. So the regular rules apply, okay? When we get to the bandwidth scaling, if it's the elements from our simple low pass filter, we divide by KB. If it's the elements that we added in, we multiply by KB. That's it. Walker. There is a combination of nano, micro, and milli. So which one are you asking about specifically? Yeah. So let's take this and let's see what happens. Okay, so let me delete this trace right here. And I'm just going to make a copy of my bandpass filter. Get rid of this thing. Move this out of the damn way. So let's put in just our regular quote unquote scaled values for here. So without the bandwidth scaling, just to make sure that things are working correctly, okay? So this would be a 50 ohm resistor. This is a 50 ohm resistor. This guy right here is 31.831 nano. This guy right here, I don't want to change the name. I want to change its value. There we go. 79.577 micro. 159.155 micro. 15.915 nano. 31.831 nano. And 79.577 micro. So what we, oh, and this guy over here needs to be 50. So when I simulate this, here's my unscaled response, right? Where we have a center frequency at 159 millihertz. When I look at this guy, it should be the exact same graph, except that it's going to be shifted over to where the center frequency is at 100 kilohertz. So That looks to be pretty legit, right? Let me change the color of this once again to red. So if we look here, center, pretty much spot on for 100 kilohertz, right? So that part works, but it looks like our bandwidth is the exact same thing, right? So our bandwidth is still just our center frequency. So now let's go through and I'm going to make another copy. And we're going to introduce the bandwidth scaling just to make sure that it's working out correctly as well, right? So this guy is going to get multiplied by a factor of 10. So 318.31 nano. This guy is going to get divided by a factor of 10, so 7.958 micro. This guy gets multiplied by a factor of 10, so it's going to look like 1.592 milli. This guy gets divided by a factor of 10, so 1.592 nano. Multiplied by a factor of 10, so 318.310 nano. And lastly, divided by a factor of 10, so 7.958 micro. Rerun our simulation. And now let's just compare our scaled version and our bandwidth scaled version. So we have the exact same center frequency, but now we can see that our bandwidth is much more narrow because we desired a more narrow bandwidth. Yes, Hojun. 1.592 millihenries. So let's go back to the math here really quickly, right? So I have my value of L2 prime, which is 159.155 micro, and then I'm dividing that by 0.1, which is the same thing as multiplying it by 10. So 159.155 micro would become 1,591 micro, or 1.591 milli. Does that? Okay. So that's all I wanted to talk about today. Yes. What do you mean by everything is happening at omega naught? Yeah, the peak value is always going to be at omega naught. So we wouldn't find omega naught from this circuit. We are designing for a specific value of omega naught. Yeah. So our table tells us effectively we could treat this as omega naught is 1 radian per second, and then we're scaling that out to something else. Yeah. Yep. So right now I'm still leaning towards a take-home portion and an in-class portion. The take-home portion I'm going to give you guys, I believe, by Thursday of this week. If there is an in-class portion, it will be next Wednesday so that it does not conflict with your 34 final next Monday.